Let's continue our discussion of Newton's laws and expand our discussion to drag forces. We've already talked about drag forces briefly when we looked at two-dimensional motion and said that a drag force would reduce our height and the x range of a two-dimensional projectile. Here we're going to expand on things just a little bit more. So when we talk about drag forces, what we're really saying is this is going to be a resistant force opposite to the direction of motion caused as an object moves through a fluid. Now, as a fluid, we mean this could be a gas, such as the atmosphere, or it could be a liquid, such as the ocean. Examples would be a brick thrown through the air will have air resistance against it, or a torpedo fired through the ocean would equally have a fluid resistance, a drag force associated with it. And as we discussed before, our drag force is highly dependent on the object's shape, its geometry. So inconveniently, F equals ma is no longer constant. We said we would apply force F equals ma to an object, and then it would feel various forces such as the force of gravity as it was moving through space, or a constant velocity in the x direction in the case of a projectile. These are no longer constant, and we have opposing forces acting on our motion. So forces here are not just static, but also depend on an object's velocity. And this makes things physically and mathematically a bit more complex. So our force is actually given by a power law in terms of our velocity. The faster our object is travelling, the more force it will receive in terms of a resistance force, and that will scale as the velocity to some power n. And this comes from our equations of fluid resistance. Here we're saying we've got some force here plus our force due to our resistance, and this will be some derivative here of m dv by dt, which will give us a function in terms of position. Usually an integration is performed and you'll end up with differential equations for an object moving through any fluid. We're not really going to expand our analysis to this, but this is the sort of equation you would expect to see of mv dv by dx here. So in terms of fluid resistance, or in most cases air resistance for the cases that we've looked at, Fv isn't a simple function, and often experimental values are needed as inputs. And you can use an approximation in most cases, an approximation given here by the resistance force being a function of velocity, and this takes into account the c values, which are constants depending on the size or shape of the object. Often this relationship is reduced down to one we should have seen before, which is for the air resistance equaling the drag force opposite to the direction of the velocity that we've applied, we should see a drag force of 1/2 c being our drag coefficient, rho being, here it says air density, but it could be any fluid density essentially, a the cross-sectional area of the object, and the velocity squared. This can sometimes be called the Prandtl expression. And of course, we can see these kinds of relationships. They don't scale quite as well as you'd think in terms of a sphere here at 0.47 not being exactly halved once you cut the sphere in half. So this is the drag coefficient and this is the shape. If we cut a sphere in half, it doesn't drop to 0.2, it drops to 0.42 here in terms of its coefficient. Cones at 0.5, cubes at 1.05, but angled cubes at 0.8. So you can imagine how this object would respond if it were tumbling through the atmosphere and constantly changing its drag coefficient. Long cylinders and short cylinders have significantly different drag coefficients, and then streamlined bodies such as teardrop shapes or wing shapes will give you very low drag coefficients on the order of 0.04 or 0.09. So our drag force comes primarily from the formula drag force here is CV to the n. Now I realise this is very similar to formula that we've seen before, but by v to the n what we mean is our drag force can increase enormously. This n is a power law, and as we approach such speeds as the speed of sound, this n will increase and continue to increase. So our force that we get back in terms of drag will scale with velocity. In this particular case, we're looking at a body falling through the atmosphere. Here, mg, here our force of drag. It's represented as a block, but we're not really going to go and look up c for the block. This could be any shape object. We're going to look at very general terms here. So, if we were to hit terminal velocity with this particular object, this would be at a point where mg downwards was equal to negative cvn upwards. As with any force, we can say F is equal to ma. This usually results in an expression just for the acceleration of the body. So acceleration will be gravity downwards minus c over m times v to the n. So what we're really saying is as the speed of the object increases, so does its drag force. And, as we've discussed before, our velocity will reach a point where the downward acceleration here is equal to the force of drag upwards. When these forces are equal, we cannot have a non-zero mass. Therefore, if the mass has some value and the acceleration due to gravity here is equal to the acceleration upwards, this means this object stops accelerating and moves at a single velocity, a velocity we call the terminal velocity. Remember, this is a terminal velocity. It's still moving with some speed downwards towards the Earth. Often people mix up acceleration and velocity here and assume the object has stood still and stopped mid-air. It hasn't. Its acceleration is cancelled. G and A here in F equals ma have cancelled, resulting in the object falling at constant velocity. So the speed of our falling object becomes constant, so mg is equal to cvt to the n here, where vt is your terminal velocity, or mg is cv to the n. Rearrange this and you'll get a relationship of mg over c times 1 over n. The reason we're using n here and not the usual squared is because if this object were falling very close to the speed of sound, then you'd end up with this n scaling to bigger and bigger values. And that's the kind of thing you do when you look at, say, a parachute. You want to maximize c, you want to maximize that drag force, and that means you want to hit terminal velocity much more quickly. So the speed of our falling object becomes constant due to resistance by the fluid that it's falling through. So let's take a look at a quick problem. Here we have a 64 kilogram skydiver falling out of a plane at terminal velocity. And its terminal velocity is 180 kilometers per hour, with his limbs spread out. What's the magnitude of the drag force? Well, we're clearly told that this situation is terminal velocity. If terminal velocity exists, we can always say that a, the acceleration, is 0 meters per second per second. This means in terms of F equals ma, that Fd, our drag force, minus mg is equal to 0. So, Fd is equal to mg. This will be equal to 64 kilograms, the skydiver, times 9.81, giving us a drag force of 628 newtons to bring about terminal velocity for this case. Now, here we've used bv squared instead of the typical cv squared. Some books use different notation, but here b is that drag coefficient c in the previous slides. Finding the value of b, Fd will equal mg, which will be bv squared, so b is mg over v squared. Making sure our velocity is in meters per second. Here we can take our 180 kilometers per hour and we're going to multiply here by 1 over 3.6 here to get this in the right order, get this in the right sense. This is kilometers per hour. We want to essentially multiply by our 180 here by 1 hour over 3.6 to get 50 meters per second. So B will equal 64 times 9.81 over 50 to give us 0.0251 kilograms per meter. And this is a slide we have seen before, where this guy is falling from the sky here. The drag force of the air upwards will equal the force of gravity downwards. Since his mass is non-zero, that means that G and A cancel. And as you can see at the very beginning of this slide, that's where these forces are unbalanced for a second, balance up due to him hitting terminal velocity, and then his velocity stays constant. His velocity increases here very briefly at the beginning of this graph. So there's the object hitting the ground, 6, 9, 10, there we go. So it's the force of the air moving around him that resists the force of gravity downwards. Practical cases. Is there a practical case of this? The most practical case I can find of someone attempting to achieve terminal velocity is the case of Franz Reichelt, a man who died in 1912. He was an Austrian-French tailor and inventor, and decided that with the upcoming advances in aviation at the beginning of the period of World War II around 1914, when more and more aircraft were being used by the military, that he would invent a type of parachute, a parachute suit. And here he is, looking very stylish, modelling his parachute suit. Now, I often have quite a lot of respect for inventors who design, build and then test their own equipment. Unfortunately for Franz here, his test of the equipment didn't go entirely well. Here he is in his equipment, not sure he asked for a lot of planning permission with what's about to happen here. But his very fine suit that was intended for French pilots to wear during the war, well, the upcoming war he didn't know about, but still, French pilots to wear on military missions, looked like this. And this is footage of him actually testing out this particular suit. And as you can see, he's standing on all of the safest, most advanced equipment, such as a chair on top of a table, accompanied by two friends. And then Franz decides to test out his parachute suit. The idea of this parachute suit is that it would be quite compact, as you saw in the first footage, and then he would open it up if he needed to escape from an aircraft, and the drag would pull you from the aircraft and allow you to descend safely to the ground. As we can see, Franz needed more calculations. He was taken to a hospital where he did actually die later of his injuries, but as you can see, he didn't exactly succeed in this particular case. The parachute as we know it was developed shortly afterwards. Of course, the use of silk in a parachute also helps it due to its lightweight nature and its resilient nature. So when we talk about air resistance, what we really mean is when we add significant air resistance to our system, we, instead of following the idealized path where our velocity and acceleration stay the same, we'll have a modified parabolic trajectory, which will be shorter in range and reduced in altitude. So, if we were to look at this kind of situation, we could actually look at the forces involved in, say, a projectile moving through the air here, and here we would have a component of the force of gravity here. Here's the weight of the object, and you could calculate lift and look at the actual forces acting upon it. But when we actually look at the air resistance for an object, then we can see that our force was scaled by the formula we saw previously, 1/2 c rho av squared. And as you can see, here's the air resistive force. This is the force that will resist the motion of an object, and here's the velocity of that object. And as you can see, the resistive force scaling with velocity here is not linear. That's that power law. For relatively low speeds that we've been dealing with, we can look at v squared. For much higher speeds, we have to look at a different power. And when you're looking at drag coefficient, often you'll see something quoted called the Mach number. The Mach number, or Mach 1, is the speed at which sound, or local sound, is actually exceeded. And as you can see, here is our drag coefficient for an aircraft's wing, and it's increasing here in the y-axis, and here's the Mach number. Here's the speed of sound being surpassed. So here's us passing the speed of sound, and as you can see, there's an enormous increase in drag as you approach the speed of sound, which drops off after you've exceeded such speed. This is due to the buildup of a shock wave ahead of the object and a massive increase that corresponds in resistive force. Now, when sound speed is concerned, this will vary in different media, meaning that the sound speed in air, here given as 343 meters per second at 20 Celsius, changes by temperature. Here it's 0 Celsius at 331. So the sound speed actually changes depending on your temperature and, because of that, by altitude. Of course, if you're in water, you're looking at sound speeds being much higher due to the denser medium. And that's where we look at sound speed as a limit to which you can move in terms of the sound that's generated by the object. Here, the speed of sound was broken by Chuck Yeager. He was the first person, of course, to break the sound barrier and live. In a lot of cases, people did break the sound barrier, but subsequently did not survive. But he broke the sound barrier on October 14th, 1947, and died only last year. Now, this man broke the sound barrier chewing gum and with a broken arm, which was relatively impressive. He did, of course, break the sound barrier at 45,000 feet, or 13,700 meters. At that altitude, the temperature of the air is much lower, the gas more rarefied, and it's a little easier to break the barrier at that altitude with a rocket plane. The sound barrier is now frequently broken by military aircraft and used to be broken by civilian aircraft such as Concorde when Concorde was still flying. Of course, breaking the sound barrier over a populated area often results in a shock wave which damages local infrastructure, breaks windows, and causes a sonic boom. The boom being the release of energy here due to the Mach cone, due to the pressure cone set up by breaking that barrier. That means that the thrust SSC car that broke the sound barrier at ground level had to have a lot more power and be a lot more technologically sophisticated in terms of the way it was operating than an aircraft at high altitude. So when we talk about velocity-dependent forces, what we really mean is we can move a particle of some mass m under the action of a force which is given as F. This is a function of the particle's velocity, but not really its displacement here, just its velocity. And a force of that type is non-conservative, and you can get from this equation ma, this is a different version of ma, m dv by dt, which is equal to the force that scales with our velocity. So our equation of motion, ma, is equal to F. If you integrate this equation, you'll end up with dv prime by f, which is equal to t over m. And you can solve that equation to get v. So you can often look at the equation of motion in much more complicated cases. We're not really going to expand our analysis to this, but this is a very useful form of analysis in terms of the equation of motion for a resistant or varying force with velocity. As you can see, this is mv, the momentum, times dv by dx. This is a practice that's often employed in more advanced physics to express many things in terms of momenta instead of just force. And solving this equation pretty much solves anything you need to look at in terms of velocity-dependent force. You do, of course, need values of the displacement and the mass of your object. Now, we do see other cases of restorative forces, resistant forces that are not fluids, that we will discuss later. One of these being Hooke's law. We've talked about Hooke briefly before, and this particular force is referred to as F equals negative kx. This is a restoring force from a spring. So take a spring and extend that spring. That spring will have a force which will want to pull your mass back, and that force will be given by a spring constant K. How much force do you get per unit extension in newtons per meter? So the restorative force will be negative because it's trying to restore the mass back to its equilibrium position, Kx. So our total force here, this is in the x, this is in the y. If we look at this all in the y direction, and this is the more typical case, and we'll see this when we talk about oscillators, we can take a mass on a spring and allow it to drop. What will happen is this mass will bounce up and down as the restorative force of the spring pulls the mass back up and gravity pulls the mass back down. The two will constantly be vying for control here. As the mass comes down, the spring builds up its energy and tries to restore the mass back to its equilibrium position, and gravity then pulls it back down and tries to also restore it to its equilibrium position, causing this mass to bounce up and down. Yes, in this particular case, our F is negative kx, negative mg. This is not an error in this case. In this particular case, what we're talking about is this is a restorative force that wants to take this mass back to its equilibrium point, its x equals 0 point. This is a negative mg that wants to take that gravity wants to also return this mass to its equilibrium point. Hence, in this case, both forces will end up being negative.